So the next topic that we're going to consider is sampling and estimation, right? And so implicitly we're thinking about, we've already talked a little bit about this story of having a population and trying to look at some kind of sample, subgroup within that population of this thing that we call a sample. And we're going to be able to say some things, hopefully, about the overall group by looking at a small sample. That's fundamentally what the topic of sampling and estimation is going to be looking at, right? So your book does this nice little thing that I wanted to include that just describes the steps to a sampling plan. I don't want to spend very much time on this, but I do want to encourage you to spend a little bit of time reading and thinking about the way that your book talks about this idea about a sampling plan, right? Because in general, it's not necessarily that you are going to be doing a lot of sampling, but still, there's a whole lot of things in here that I think are related to the concept of critical thinking. And so in general, right, I think that's what analytics does really well, is develops skills related to critical thinking. But again, I'm not going to spend too much time on this sampling plan. I do want to mention that there are many different ways that we can sample, right? We alluded to this in the past. It's really, really good when we've got a random sample that is representative of the overall population. And there are different ways that we can try to do sampling, and some of those might be a little bit more representative than others. And so I'll just lay that out as a statement of fact and let you go ahead and consider the text for a few more details related to that. All right, some terminology that we want to focus on. Estimation. When we do an estimation, what are we doing? We're assessing the value of an unknown population parameter. So again, right, when I think about my population, there are many different parameters that can describe different attributes of my population. But we don't know those, right? Oftentimes, we will never be able to observe an entire population. So rather, what we're going to do is we're going to look at a subsample of the population and try to make some inference about what's going on with the overall population. That's what the process of estimation is. We're trying to assess a value in our population that we oftentimes will not be able to observe, and we do not know it with certainty. We've got two different types of estimation that we're going to consider. A point estimate is a single number derived from a data sample to estimate a population parameter. These are things like X bar, right? Or our standard deviation. You've done these kinds of things, right? When you calculate the mean of a sample of data, which you've done in this class already, formally what you were doing is coming up with a point estimate, right? A point estimate is what? It is a single value. So anytime that you were doing an estimation and you were resulting in a single value, that's what we call a point estimate. Whereas an interval estimate is something like a confidence interval, which more than likely you may have done this in a previous class. A confidence interval, right, has two different numbers. It's got a lower value and an upper value, and it covers some range of values related to the population parameter, right? So again, confidence intervals, and maybe there's a few other ones that you might have done that are similar to that, are some interval estimates. Again, you've probably done these before. We're just making sure we have the terminology for it. Unbiased estimator. So an unbiased estimator is a true estimate that repeated experiments in the statistical group population parameter. What does that mean? So if we care about the average price of popsicles in the US, we are never going to be able to observe the population of popsicle prices in the US. But what we could do is we could take a little sample of, say, 50 stores, and we could go to those stores and figure out what the price of a popsicle is. And if our sample is unbiased, then it means that the average of the sample is reflective of the true average of the population, right? An unbiased estimator means that our estimator is representative. It's not above, it's not below, it's right in the middle of what the true value for the population is. So to think about what a biased estimator is, an unbiased estimator is one that gets it right, so to speak. A biased estimator is when we have an estimator and it does not give us the true underlying value. So I've got this as a thought experiment, right? So what if I tell you that this is a foot, and I ask you to measure with this ruler the size of the room that you're in. Say that you're in a 12-foot room. If you go ahead and you measure this thing out, gosh, if you look really, really, really closely, notice I lied to you. This is not 12 inches. This is not actually a foot. But if you counted up this as a number of feet, right? Normal rulers that are a foot long are only 12 inches long, right? I'm assuming you knew that, right? So this is going to give you systematically an incorrect piece of information. You could do a sample, you could take a measurement of the size of the room that you're in, and everyone could do a measurement of the size of the room they were in, and if we looked at that sample of the size of the room, right, it would not be reflective of the underlying truth because there is some bias. That specifically is a bias in the way that we measured, right? So the next topic that we want to talk about is a little bit big. It's called the central limit theorem. You may have seen it before. What I want to do is I want to flip over to Excel and spend a little bit of a time in Excel talking through some examples and working through some new formulas and some new things that we can play with in Excel. So go ahead and open up a version of Excel, and then we'll pick up the central limit theorem from there. Okay, so we want to spend a little bit of time in Excel exploring this concept of the central limit theorem. The central limit theorem says something about the distribution of observations. And so you're probably familiar with a few distributions like the normal distribution or the uniform distribution or the binomial distribution. We looked at a bunch of those in the last topic, right? So one of the questions that we can do is how can we show these distributions or do random draws from a distribution in Excel? Under the Data tab, to the right under Data Analysis, and again, look earlier for that add-ins option for when you can do bring this up as part of your Data tab. There is an option called Random Number Generator. As its name implies, the random number generator is going to generate a random number from one of those distributions that we care about. So real quick, notice distributions, right now it's set on discrete, but I can do a uniform distribution or a normal distribution or Bernoulli or a binomial or a Poisson or a discrete, right? I've got a bunch of different distributions that I could consider, right? Let's go ahead and pick a uniform distribution to begin with, right? So what are some of the options in this dialog box? The first value, number of variables, that's going to be the number of different columns, right? Let's go ahead and just set that equal to 1. Right, so that's saying we're going to have one variable that is draws from one single distribution, and right below that it says number of random variables. This is going to be the number of random draws. Let's go ahead and set it equal to, let's go ahead and just do 100. So that 100 is going to count up the number of rows, and each of the rows represents a different draw from a random distribution. Let's go ahead and set our uniform distribution. If you recall, what does a uniform distribution look like, right? It looks like, can I ink on that? No, I can't ink while I have this up. A uniform distribution looks, oops, I got to go ahead and get me back to a pen. All right, so a uniform distribution is the flat distribution, right? Where everything is equally likely. Every value has an equal chance of occurring, right? And so to define a uniform distribution, here's a nice little picture of it, right? You need to know what the lower value is that starts the distribution and what the upper value is. So if we go back to Excel, right, let's go ahead and have our uniform distribution between 0 and 100. So basically, this is going to generate some value, some random value between 0 and 100, and all values are equally likely. Under random seed, so go ahead and just enter any old number that you want in there, right? What this allows, the point of the random seed option is that you can allow comparison across different computers, right? So if I put 450 and you put 450, we should the random process should generate the same set of random numbers. If I put 450 and you put 460, then you are going to be pulling a different set of random numbers. But if you want to follow along with me, go ahead and pick 450. And then I've got some options in terms of where this is. Let's go ahead and select output range, and let's go ahead and put it in cell A1, right? So again, make sure yours follow mine, and I'm going to click OK. And what does it bring up? It brings up a single column, right? So I've got from a single uniform distribution, if I scroll all the way to the bottom of this list, I've got 100 random values. But notice how many decimal places there are, right? So this literally was going between 0 and 100 from a continuous uniform distribution. If I just ask you to pick a random number between 0 and 100, you probably were not going to say 4.60219. No, you weren't going to say something like that. So maybe we want a random integer between 1 and 100. How could we go ahead and do that? Right, so let's go ahead. And the way that we eliminate the decimals are by rounding. So, so we've got the round is a function, and if I select the number that I want rounded, comma, the second parameter in the round function tells me how many digits. And let's go ahead and just have 0 decimal places. And so it's going to tell me 5, right? It took the number 4.602 and rounded it up to 5. And so if I just copy that down the entire list, then what do? What do I have? I have 100 random observations, random draws from a uniform distribution, right? So think about this for a second, right? We go back to the Excel, or to the graphic of this. If this distribution starts at 0 and ends at 100, and everything has an equal probability of occurring, right? This is theoretically what the distribution would look like. What we just did in Excel is we generated an empirical distribution of this thing, right? We drew a bunch of random draws from this. What if we just decided to look at a quick histogram of this data? I select all my data, and under the insert, I've got my recommended charts, and histogram is an option. When I click on a histogram, I think I want to adjust some of these options, right? So let's go ahead and try to adjust. I can also use this as a drop down, right? For my axes title. All right, so if I go under my axes, that little line to the right gives me a couple of different options. And so now this brings up, these are the options that I was looking at, right? So we've got different elements of the chart, and one of those, right? So what it's doing is the bins are the different categories that it's measuring horizontally, right? We've got a bunch of numbers between 0 and 100, and what this is doing is this is figuring out how many different categories to lump those observations into. It's automatically choosing 5 bins, but I can also adjust some of these options, right? So what I've got there, right, is I can either set the bin width, which again, notice 20. I've got 100, so 20 divided by, or 100 divided by 5 is 20. That's where that comes from. I can either adjust my bin width, or I could also adjust the number of bins. Let's go ahead and adjust the number of bins to 1. Let's go 10, just for beginning, right? Right. And so this basically looks at in 10-unit increments, right? 0 to 100, 10-unit increments, the number of random draws that happen. Now, again, think about this conceptually, right? A good little question for you to think about is, if we've got 10 bins and I have 100 observations, on average, how many observations would you expect in each of the 10 bins? So we've got this distribution, and this is with 10 bins. We can adjust. What if we made the number of bins 100? Before I click OK, go ahead and think about what you expect this graph to look like. On average, you'd expect, if we have 100 bins that each are, 1-unit increments, you'd expect to have about 1 observation in each of the bins. But notice, right, with just some random luck of the draws, my goodness, in the random distribution that I did, I had one of my bins that had 5 observations. Notice I also had a number of bins that had 0 observations, right? You could think about, does this empirical random draw from a uniform distribution, does its pattern somewhat look like what the theoretical is? It looks kind of like it, right? But it's a little bit different. So we can think about, in Excel, what if we tried to change some of our options? What if we go back under the our data tab in data analysis, bring up our random numbers? What if I change this 100 to 500? What am I doing? What I'm doing is I'm going back, and instead of doing 100 random draws, what if instead I looked at 500 random draws? When I do that, oops, and I've got to overwrite my data into it, no worries. What does it do? Well, I didn't have my formula all the way down my sheet, so I got to go ahead and click my formula all the way down the sheet, and then go back, and now when we have, whoops, sorry, we got to copy this down so that it's covering, I can scroll to the bottom of my list. Now I have my 500 random observations. If I create a little graphic of that, not a graphic, but a histogram of that, I guess a histogram is a kind of graphic, right? Then again, I can adjust some of my axis options. I've got, yes, go away. Number of bins, if I set that again equal to 100. When I had 500 observations, it looks like each of the bins, some of them have 0. My goodness, 0 observations between 24 and 25 out of this group of 500. How likely is that? Similarly, we had some bins that were all the way up at 10, right? But it looks like the average number of observations in a single bin is somewhere around 5. And right, you think about that logically, that's to be expected. So let's go ahead and swing back and revert this to just a single group of 100 observations, right? So so I am just going to go ahead and take everything after 100 away so that we're back to our initial story of having our 100 random draws. Nice little histogram. Do you have a preference on the histogram that you've been looking at in terms of how you would go about how many bins? Do you have a personal preference? I think the nice thing about this, right, is that if we've got 100 bins, we can clearly see, right, exactly how many observations are in each of the bins. But is that a really useful histogram? What if instead we only did 20? If we do 20 bins, even that, I'm not sure that looks good. What if we do 15 bins? Maybe 15. I kind of like 15, right? Again, this is a little bit of personal preference in terms of what visually you think looks good. Clearly, doing 100 bins is probably overkill, and if we also did 1 bin, that's not a useful graphic whatsoever as well. Neither is 2. Though 2's not surprising, right? If we divide this in 2 different bins, notice they're not quite equal to each other, right? We don't quite have an even distribution, and you'd expect that with these random draws. Sometimes by random chance, we've got a few more observations that are over 50 rather than below 50, right? So 10 bins also does a nice job of this. This generally looks like a uniform distribution, right? So if we had a uniform distribution that started at 0 and went up to 100, you could think about what would be the expected value, right? Real quick, follow-up question. What is the expected value of this uniform distribution? Remember that you can think about the the expected value as it's like the balancing point, right? If you were to put your finger on the bottom of this distribution and try to find the place where it balanced, where would it be balanced? There's also some equations in your book that describe what the expected value of a uniform distribution is, or you might be able to think about that and just logically come through or calculate what you think the expected value is. Recall that the expected value of something, and oftentimes, right, we can just shorthand expected value with the letter E. The expected value of this distribution is equal to the probability weighted average of the outcomes. But remember that in a uniform distribution, all values have an equal probability of occurring. And so that has some special implications for the way that you calculate the average when each are equally likely to occur. If we go over to our distribution, right, so we see that this is not quite a uniform distribution, but we can go ahead and get rid of that. If we calculated the average of these 100 draws that were from a uniform distribution, what kind of average would you get? In essence, that's what the expected value is, right? Is this number surprising to you, right? hopefully you came up with the fact that a uniform distribution between 0 and 100 is going to have an expected value of 50. Theoretically, the expected value is 50. From this random distribution, the expected value is actually 52.14, right? We looked at one of the distributions, one of those histograms, and saw that there was a little bit over-representation of values greater than 50, so it's not surprising that this number is a little bit north of 50, right? We looked at one set of 100 random draws from a distribution, right? I want to go ahead and delete all of this and then think about one other thing that we can do. Actually, we're going to think of a number of different things that we can do. But let's go onto that data tab again and do data analysis, bring up the random number generator, and let's stick with the uniform distribution. What if instead of doing 500 draws, what if instead we did one draw? One draw from a random, one random draw from a uniform distribution is going to be one draw from a random distribution. It's going to be any number between 0 and 100 equally likely. The next step to this is we go back to our random number generator, and what if instead of that first number, right? We've always had it looking at one single column, one single variable. What if we change that to the number 5? Then what do we have here? Yeah, let's go ahead and overwrite it. What we have is we have 5 columns, and each of those columns represents one single draw from a uniform distribution, right? What if I looked at the average of this group? All right, so this is a little bit ridiculous, but what if I calculate the average of column A? Not surprisingly, the average of one draw from a uniform distribution is just the value of that distribution. And if I copied that average, so I was looking at the average of each of these 5 random draws, each of these 5 columns of a single draw from a uniform distribution, what we're going to have is a bunch of random numbers between 0 and 100. If I ask you to do a histogram that showed the distribution of these averages, it's going to look exactly like this distribution, right? This is a little bit strange, but stick with me for a second, right? If we've got a single draw, each of those draws are equally likely between 0 and 100, so the average is just that number. If I ask you to do this for 5 different columns, and then ask what would the distribution of those averages look like, those averages are just going to be all equally likely to occur between 0 and 100. So those averages are all also going to look like a uniform distribution. Now here's where we change the story. What if instead of doing a single draw from a distribution, what if instead when I do my data analysis random number of variable, what if I still do 5 columns, but now for each of those columns I do 2 random draws from a uniform distribution of 0, 100. When I do it, yeah, go ahead, overwrite that, sure. What do I have? Now I've got 2 values in column A, 2 values in column B. What if I went ahead and also calculated the average? If I calculate the average of these 2 values, what's going on with the average there? A1 through A2. I don't know what's going on with my cursor there, right? The averages, if I looked at all 5 columns of the average of 2 draws from a from this uniform distribution, what would it look like? Would the averages look like this anymore? No, right? So it's going to be very, very unlikely to have 2 numbers that are very, very small or very, very large, and it's much more likely that this thing is going to have a little bit more representation in the middle than at the ends, right? And we could further explore that in Excel. But notice that randomly, sometimes we are going to have 2 large numbers or 2 smaller numbers. What if we take this the next step further, right? Under our data tab with our random number generator, and we still look at 5 columns, but instead of doing 2 random draws, what if we did 25 random draws from a uniform distribution between 0 and 100? Yep, of course, overwrite this, right? Then go down to the bottom of this column, and if we calculate the average, Right, so we can do under the formula, we've got that automatic nice little one. Let's do the average of my list. If I take that average of the first list, copy it to the right, notice, what do you notice about these averages of these 25 random draws from a uniform distribution? 42, 65, 54, 44, 54. If you did the distribution of the averages of 25 random draws from a uniform distribution, it's going to be amazingly unlikely that you get something towards the end, right? You're going to have much, much, much more common that the averages would be somewhere in the middle. In fact, it might start look something like this, right? And again, the point of this is that the more observations we keep adding to the column, the more random draws that we have, the closer the distribution of the averages comes to looking like, does this guy look familiar? A normal distribution, right? That's really the point of the central limit theorem, that as we increase the number of observations of random draws from a distribution, the more normal the distribution of the averages, not of the individual observations, but of the averages. The more the distribution of the averages looks like a normal distribution. What we just did is we just told this whole story with a uniform distribution. But what the central limit theorem says is if we go under the data tab, right, random number generator, what we can do is instead of looking at a uniform distribution, what if instead we look at a binomial distribution, right? So if you recall, with a binomial distribution, we need the probability of success. Let's have the probability of success be 0.33, right? So these are the odds of observing something. It happens 1 out of 3 times. So if we do, we also need to define for a binomial distribution the number of trials. So let's say that something happens 1 out of 3 times. If we do 30 trials, then we'd expect on average to observe about 10 successes, right? What we're asking Excel to do is calculate the number of successes 25 times for 5 different binomial distributions. Go ahead and click OK. Click OK. And then we've got all these numbers. And notice, right, if you just go ahead and look at column A, right, let's go ahead and quickly scan through that list and then do a little histogram of it. That if we've got a histogram of it, we need to adjust the bins to see this a little bit better, right? Under our axes, I want to adjust the number of bins. Let's go ahead and make the number of bins 10. Can you see? Right? Does this very much fit, or what if we do 15? Is that going to see? Nope, 15. Whoa, 115 is clearly too much. 15, maybe a little bit. I don't know that I like 15 as well. What if we do 7, right? So there's a little bit of an art with this, not just some basic scientific stuff, but there's a little bit of art to trying to figuring out visually what works best, right? Theoretically, do you know what a binomial distribution looks like, right? It should have this kind of pattern to it where it's very, very, very unlikely to have a small number of observations, but it's possible to have something like this, right? Binomial distributions, if you recall, a binomial distribution looks something like this guy right here, right? So if we take our binomial distribution and we calculate the average of it, notice the average is about 10. But sometimes it's a little bit above 10, sometimes it's a little bit below 10. If we do this distribution of the averages of 25 draws from a binomial distribution, what it's going to produce is it's going to produce something that looks like a normal distribution. Part 1 of the central limit theorem. It doesn't matter what the underlying distribution was that generated a single observation. It does not matter what the underlying distribution was that produces a single observation. If we look at the sample average, it's going to follow a normal distribution. It doesn't matter what the underlying distribution was that generates a single observation. the distribution of the sample averages is going to look like a normal distribution. That's big part one of central limit theorem. Other part two of central limit theorem is, as we increase the number of observations, we usually use n for number of observations, as we increase the number of observations, the distribution, this looks more and more normal and gets skinnier. The variability changes. It gets smaller as we add the number of observations. And it changes in a very, very predictable way. Those are the two parts to the central limit theorem, right? That are observations. No, it doesn't matter what the underlying distribution was. The distribution of the sample averages always looks normal. And as the number of observations increases, the variability decreases in a very predictable way. We had mentioned earlier confidence intervals. Now we want to formally do it. So a confidence interval is an example of an interval estimate, right? It's got the word interval in it. It's a range of values between which the value of the population parameter is believed to be along with the population probability that the interval correctly estimates the true unknown population parameter. So we've got this, this level of confidence, which we define as 1 minus alpha. Alpha is going to be a value between 0 and 1, right? And so you may recall calculating a 90% confidence interval or a 95% confidence interval. Let's consider a 90% confidence interval. What is the value of alpha for a 90% confidence interval? We can talk generally, this formula, a certain percentage confidence interval for a population mean, mu, based on a sample size n with a sample mean of x bar and a known population standard deviation sigma is this, right? So let's talk through the different pieces to this, right? So x bar, again, big picture conceptually what's going on, we've got some kind of population and we care about a population parameter. The one that we care about is the mu, right? So we care about the mean of a population. And what we do is we look at some kind of sample, right? We're looking at a small sample, a subset of the population, and in that sample we can calculate what the average of that sample is. That's what x bar represents, right? It's the average of a sample. Our best guess for what a population parameter mu is, we take our x bar and then we're going to add some uncertainty to either side of it. That's why we've got the plus and the minus, plus minus, and this next term has three parts to it, right? It's got a value of z, right? So z alpha over 2, z is the value that comes from a standard normal distribution, right? We talked about a normal distribution having the four properties. Do you recall what they are, right? Mean, median, and mode, all the same. Symmetric, value of our variable is positive infinity, negative infinity, and it follows the empirical rule. Z is a special kind of normal distribution where in a standard normal distribution, the average is set to 0, right? And so you can also normalize by setting something equal to 0. And if we look one standard deviation out, it's equal to, or it's set to, or adjusted to a value of 1, right? One standard deviation out is a value of 1 on either side. So that's a special kind of normal distribution called a standard normal distribution. And z is simply a value that's associated with something and our alpha over 2, right? So our alpha over 2 is the amount of probability outside of the value of z. Z is a certain value where the probability on either side of z, the negative or the positive, is equal to the alpha, right? And so we split that probability in the alpha between the two different parts. That z corresponds to the value related to this level of alpha, right? And then this last term, we've got the sigma, which is, I think this is really interesting, right? Sigma is the population standard deviation. Remember, the standard deviation tells you about how spread out the data is, but sigma is the spread of the data in the population, right? It's actually not that common for us to know what the value of sigma actually is. Remember that sigma is a population parameter, though. It's talking about, for the population, how spread out the data is. That's oftentimes not a variable that or that's not a value that we're actually not going to be able to observe that often, right? It's very, very rare that you are going to know for certain exactly how spread out the data in the population is. Rather, it's much more likely that within your sample, you might be able to estimate your sample standard deviation, and that might give you some hint about what the population is. But this formula right here for this confidence interval is based on knowing for certain what the standard deviation, the population standard deviation it is. Oftentimes that's not the case, but that's what this equation is looking at. And so in our denominator, we just divide that by the square root of the number of observations. And again, z is the value associated with the standard normal distribution, the value of z that is consistent with taking whatever the alpha is from the size of our confidence interval and spreading it. So, follow-up question, right? If, let me clean this picture up a little bit and then ask the question, if we had presented a 90% confidence interval, right? So I go ahead and do my normal distribution, and a 90% confidence interval has an alpha of 0.10, right? A 90% confidence interval has an alpha of 0.10. If I take alpha over 2, split it in half, because I've got a symmetric normal distribution, that'd be 0.05. So if I take my 0.05 over here and put my 0.05 over here, the value of z that's associated with, from a normal distribution having 0.05 probability to the left and 0.05 probability to the right, those are those values of z that correspond to 0.05. What if instead of having a 90% confidence interval, here's my question, what if instead of having a 90% confidence interval, what if we had a 95% confidence interval? Will the value of z be to the left or to the right of this point and this point? Will it be closer to the middle, or will it be further out in the tail when we have a 95% confidence interval? I want to consider how to estimate a confidence interval in Excel, and we're going to do this the long way first. So let's go ahead and let's bring up this Dow Jones Industrial Average data that was available, and let's go ahead and delete everything before 2019. So that I am just looking at values in 2019. And notice we've also got some NAs, and I believe that those are days of the week when the markets aren't open for certain holidays. Notice that we've got some, this usually runs Monday through Friday, but there are certain days of Monday through Friday that are national holidays, or days, I should say more generally, days that the Dow Jones Industrial Average is not open. And so I've got this. I'm going to go ahead and organize this data a little bit more cleanly. Okay, so real quickly, what I did that took a little bit of time, so I didn't want to waste a video time, and it was I deleted all the dates and values of Dow Jones Industrial Average that were undefined, and then I just highlighted my data and I sorted it by the observation date. And so what that did is that put everything in a row, everything in order of close, and it also brought it up to the top. And so what I want to do in column C is I want to just calculate very, very simply this real quick. What is this calculation doing? This is just calculating the change in the Dow Jones Industrial Average from one day to the next. So this, copy it down the entire list. We could title this is the daily change in Dow Jones Industrial Average. For the year 2012, nope, 2019. Can we jump to the bottom of this list, and can we calculate two things? Number one, let's go ahead and calculate the average. Perfect, right? And so this is going to tell us the average change in the Dow Jones Industrial Average for this data set that goes through towards the end of May of 2019. Geez, what was the average change? Only $22, right? We got a lot of negatives, we got some positives, but overall, there's an upward trend to this, right? But it is not a very, very strong upward trend to the Dow Jones Industrial Average over this time period. Can we calculate a 90% confidence interval for this? Recall, for the confidence interval, we need 4 different pieces of information. We've got one, right? We've got what the sample average was. What's another piece of information? We need our z alpha over 2 value. We also need our standard deviation. And we also need the n number of observations. Okay, so how can we get some of this stuff? Number one, the z value. So if you recall, what did I ask for a second? Let's do a 90% confidence interval. So if I have a 90% confidence interval, that must mean that my alpha value, alpha would be 0.10, and so alpha over 2 is 0.05. Right? 0.05 is the value of alpha over 2, which is what we need for a 90% confidence interval. And again, conceptually, what we're thinking about is we are thinking about a normal distribution, a standard normal distribution, where 0.05 probability is to the left of this value. And we're also going to look for the value that has 0.05 to the right of it, right? But realize that because the standard normal distribution is centered around 0 and it's symmetric, those two values of z, one's going to be negative, one's going to be positive, but the value, the magnitude should be the same. Also remember about a normal distribution, think about what the empirical rule said in terms of being 1 standard deviation, 2 standard deviation, 3 standard deviations. Can you give it a sense of what kind of value this might be? Let's go back to Excel and try to figure out how to find that value of z from a normal distribution. Here we go. If I do equal and I do norm for a normal distribution, I've got a couple of different options to the left that I want to talk through, right? So I've got norm dist, norm inverse, and then I've got 2 below it, norm.s.dist and norm.s.inverse, right? So the first 2 are in general any set of normal distributions, and the set below are specifically standard normal distributions where the average is set to 0 and the standard deviation is normalized to a value of 1, right? So the distribution values return the normal distribution for the specified mean and standard deviation, whereas the norm inverse gives me the inverse of the normal cumulative distribution. All right, what does that mean? Let's go ahead and do one of these. Let's just do norm dist first, and notice that I've got 1, 2, 3, 4 different parameters here. Let's have our value of x is going to be the value on our distribution. So it's the value of the thing we're measuring horizontally here, right? If we knew the value of this, the norm.dist would tell us the probability up to that point. So for example, if I've got, actually let's come back to this. Let's start with norm.inverse. What norm.inverse is looking for, right, for its parameters, it's probability, mean, standard deviation. So norm.inverse tells me if I know a certain probability, it will return the value horizontally, whereas norm.dist goes the other direction. If I know the value of my x, it will return back the probability associated with that. So we want how much probability to the left? Let's go 0.05. And a standard normal distribution has a mean of 0 and a standard deviation of 1. And so if I close out my formula, it returns a value of negative 1.64. And again, if you think about that empirical rule, is a value that's going to have 0.05 to the left, 0.05 to the right, is that value going to be somewhere between 1 and 2 standard deviations? That's what that's telling you, right? So the z-score is telling you how many standard deviations normalized where the average is 0 and the standard deviation is 1. This is between 1 and 2 standard deviations. That fits for the empirical rule, right? The empirical rule says that if we go 2 standard deviation outs, we're only going to have 0.05 on either side of that. So if we've got 0.10, then we'd expect it to be somewhere between 1 and 2 standard deviations, right? The z-value, negative 1.64, that's when we were looking for a probability of 0.05. So the way that Excel is constructed is that value of probability that you enter into that formula, it tells you the value of x with the probability to the left of that point. That returned the value of negative 1.64. If I want to find this value on the right that has 0.05 to the right, how much probability is to the left of that point that has 0.05 to the right? It's got, right, similar but different structure, equals norm.dist, inverse probability 0.95, right? If I'm looking for 0.05 to the right, then how much of probability is to the left? It's 0.95. And I've got what for an average of 0 and 1 on a standard normal distribution, and this should return a positive value of 1.64, right? So those are the z-values that are associated with a 90% confidence interval. Think about if I were to change this to a 95% confidence interval, my alpha over 2 would become smaller, right? It would be 0.025, and then what do I need to change with this formula? I would need to change this. And not surprisingly, right, intuitively this makes sense, that if my value of alpha gets smaller, if my confidence interval goes from a 90 to a 95% confidence interval, that means that my value of alpha has gotten smaller, and that would mean that even less of my probability is to the left, so we'd expect a value of z that is further out in the tail. A 95% confidence interval would have this as, and yep, that's a value that's closer to -2, which fits with our expectations from the empirical rule, right? But again, let's do a 90% confidence interval. Jump down to the number of observations. One quick way to do the number of observations in Excel is there's just a count option, right? So I can just count the number of observations that are here in my data set. And so notice the cells that I selected, and it automatically generates 99. There were 99 observations of Dow Jones Industrial Average Close. That's what my N is, right? So now here's the problem, right? Is what I need to do is I need to calculate my standard deviation. But if you recall, right, this is the formula for if I know the true underlying variation from my population. Oftentimes I'm not going to have that, and instead what I can use is just simply my standard deviation from my data. And so let's go ahead and select all of my data, and the spread, my goodness, look how big that standard deviation is, right? And again, what's the calculation that I'm dying to do right now, right? That's a very, very big spread of the standard deviation. If I took that spread of the standard deviation and divided it by the average, think about, what is that thing called? Isn't that the coefficient of variation? Think about how big that coefficient of variation is and what that implies for the amount of variability relative to the average that there is in this Dow Jones Industrial Average calculations. Okay, so my confidence interval, right? My 90% confidence interval, I've got the lower value. What the lower value does is it takes the average, and it is going to, I'm going to plus the negative value to subtract the value of z times what was in the numerator of that formula. It was the standard deviation divided by the square root of the number of observations. The bottom value of a 90% confidence interval, negative 10.95. How about the upper end of the interval estimate for the 90% confidence interval of the Dow Jones Industrial Average Close? That again takes the average, and now I'm going to add the value of z, in this case the right hand side was the positive 1.645, times the value of the standard deviation divided by the square root of the number of observations. So I would write this out, that the confidence and 90% confidence interval for the Dow Jones Industrial Average close for this time period, negative 10.95 to 56.20, right? So that is a 90% confidence interval for my data set. Think about how this would change if we had a 95% confidence interval. Similar, but a little bit different, is constructing a confidence interval when we don't know what the standard deviation of the population is. If the standard deviation of the population is not known, which is going to be the case for many data sets that we're looking at, instead of using that formula that we just walked through, we use something very similar to it. We just adjust. Rather than using a z value from a standard normal distribution, instead we use a value from what we call a student t distribution, or the t distribution, right? The t distribution looks something like this. My goodness, does that look like a normal distribution? It does, right? The student t distribution and the z distribution look very similar to each other. The difference is, right, that the student t distribution might look something like this. Oh boy, I don't know if I drew that well enough, right? In general, what I try, let me try that again. The student t distribution versus the normal distribution. So if this is my normal distribution, a student t distribution is going to look something like this. It's a little bit exaggerated, but what I was trying to do was right down here, I made the tails a little bit fatter, right? So a student t distribution has a little bit more probability farther out in the tails, right? What the student t distribution is it's the correct distribution to use when we don't know what the underlying spread of the data is in our population. We've got our population, there's some spread in it. If we don't know what that value is, that's an additional source of uncertainty that we're dealing with. And so that's why the t distribution has a little bit fatter tail to account for this little bit of extra uncertainty of not knowing what the true underlying spread of the data in the population is. All that said, notice that this formula looks very similar to what we did. We've still got x bar, right? So we've still got our point estimate plus or minus this thing to the right. We call this the margin of error, right? It still has a margin of error that has 3 components to it. But we just made it a little bit of a tweak, right? We still have the square root of the number of observations. That's great. And now all that we're doing is, instead of using the population standard deviation, we're using our sample standard deviation. Is that actually what we were doing when we just went through this calculation in Excel? It was, right? So we've already moved on to that piece. The only thing that's different is this value, right? So the t distribution, right? This is using the value of t for alpha over 2, similar to z alpha over 2, from a t distribution. The t distribution has 2 different parameters that we care about. Number 1, the value of alpha, which we find the exact same way as what we did with a normal distribution. If we have a 90% confidence interval, alpha is 0.10, and so alpha over 2 is 0.05, and all we're doing is saying from that in green, that student t distribution, what's the value of t such that we've got 0.05 probability to the left, and the value of t such that it's got 0.05 probability to the right. So that in the middle is encompassing 0.9 probability, right? T distributions, like the z distributions, right? Normalized value of 0, and we normalize the standard deviation being equal to 1. Right, so the student t distribution, but there's another thing, right? There's not a single student t distribution. There's infinite numbers. Each of the different t distributions depend on this thing right here that we refer to as the degrees of freedom. DF for degrees of freedom. The degrees of freedom correspond to something about the data set and the underlying distribution. We find the degrees of freedom by taking the number of observations in our sample and subtracting 1. That's going to generate the number of degrees of freedom for a t distribution. So in general, if I've got 2 different t distributions, let me do 2 different t distributions. The t distribution that looks closer to a normal distribution is one that has a higher degrees of freedom. As we increase the number of degrees of freedom, a t-distribution is going to get closer and closer to what this normal distribution looks like. So real quick, we're going to hop back to Excel and reincorporate some of this new information on calculating a 90% confidence interval for the change in the Dow Jones Industrial Average when we don't know what the underlying standard deviation is. Hey, I've got the same thing as what I had before. I've still got the same sample average. I don't change that. I still have the same number of observations. I still have, right earlier, we were calculating the standard deviation. We are already calculating that, right? That was the standard deviation of this sample. The only thing that we need to change when we don't know what the true underlying population parameter is, instead of having a value of z, we need a value from the t-distribution that has a certain number of degrees of freedom. How many degrees of freedom is this? Again, if you recall, number of degrees of freedom is the number of observations minus 1. We have 99 observations. So this is, we're looking for the value of t that has an alpha of 0.05 with 98 degrees of freedom. So recall, we had norm.inverse was the way that we calculated the value of z from a normal distribution to get the value of t from a t-distribution. Type the letter T, and notice it brings up a couple of different options, right? And so I've got a couple of different options there with the t-distribution. That's what I want to use. The t-distribution is what I want to use if I know the value of t and I want to find out what the associated probability is. I use my t-distribution. If I go the other direction, right, and I know the value of probability, which I do here, that I want to the left-hand side, I use my t.inverse. So let's go ahead and select that one. And notice there are only two parameters that it's looking for. Number one, the probability. Number two, the degrees of freedom. And again, the way that Excel is built, when it's asking for a probability, right, I've got my t-distribution, it'll look something like that. The probability that we're entering is going to be the probability to the left of the point that we're looking for. So that left-hand value, or that left side value of t, the negative value of t, I'm looking for probability of 0.05 on that. So let's go ahead and enter 0.05. Number of degrees of freedom. Remember, that was equal to n minus 1, so 99 observations, 99 minus 1. Oh my goodness. Are you surprised at that value? Notice that the value, when we had 98 degrees of freedom, the value of our t-distribution is negative 1.66. Do you remember what the value of the z-distribution was? My goodness, that was 1.645. There's not a whole lot of difference between those numbers. Real quick, just as a thought experiment, go ahead and change the number of degrees of freedom to 10. Again, as we reduce the number of degrees of freedom, as we have a smaller number of observations, that number gets further and further away from the normal distribution. But, right, as conversely, as the number of degrees of freedom gets larger, this number gets closer and closer to what the z value was. Let's go ahead and do 200 degrees of freedom. At 200 degrees of freedom, we're at negative 1.65 instead of negative 1.645. It's pretty close, right? So there's not a whole lot of difference between these two as we get a large number of observations. It's only when we have a small sample size that we really see a big divergence between our z and our t value. What was our degrees of freedom? 98. And correspondingly, on that right-hand side, right, we've got to change from a norm dot inverse, let's do t dot inverse. And again, my probability, if I'm thinking about the right-hand side of the t, I'm looking for the value of t that has 0.05 to the right. So in Excel, what I need to enter is how much probability is to the left of that point. So I want to add 0.95, and my degrees of freedom, we had 98 degrees of freedom. And again, it's just giving t-distribution is symmetric and centered around 0, so not surprisingly, it's just the positive of this value. Notice my 90% confidence interval. How did my 90% confidence interval of a t-distribution compare to the 90% confidence interval from a z-distribution? To finish out this discussion, right, so we are primarily going to be focused on confidence intervals with continuous variables. But we can also do confidence intervals for proportions. We've been primarily focused on confidence intervals for a continuous variable, but we could also look at confidence interval for a proportion. We see these a lot around public opinion polling, right? When you've got something like an election coming up and they talk about all these polls where they do a random sample of individuals on what candidate they're going to support, something like that, then that's oftentimes where you see proportion. You also see proportions used a lot in marketing research, right? So in marketing research, when they're looking at maybe some different categories that people might answer, not necessarily a continuous variable, but different categories about how they feel about different variables or different cross tabs in terms of the number of customers that show up, that's where we might see a confidence interval for a proportion. The way that we estimate a proportion from a population, we just look at how many observations do we have, and we're just simply counting up the number of observations with a given attribute. And so we're really just looking at that x over n. That's a way to calculate the proportion of our sample which fits a given criteria. The proportion of our sample which supports Donald Trump rather than Hillary Clinton, I think is what that poll was, right? Proportions. We think of it as a percentage, but formally proportions come out to be decimals, right? That structure of the confidence interval on a proportion looks very, very similar, right? So we've still got p hat represents our estimated proportion. So if we just looked at our sample, right, what portion of our sample fits a certain criteria, that's what p hat is. Z, here for proportions, we actually use the z distribution. We're not using the t distribution, but we're using the z, but same thing again. If we're doing a 90% confidence interval, the alpha associated with that is 0.10, and so what's the value of z for 0.05? You should be able to find that in Excel, right? And then all that we do for this other part, this other piece of this margin of error, is we're taking the full square root of this entire term, not just the square root of the n, but the square root of the term p hat times 1 minus p hat divided by the number of observations. And so again, this confidence interval on a proportion should be relatively straightforward. And so my follow-up question to you is, can you real quick go ahead and use Excel to calculate a 95 and a 95% confidence interval for when we do a random sampling of 100 people, finding 45 people who we consider a success. Let's think of defining success as being who like a product. What's a confidence interval, 95% confidence interval, for the proportion of our sample that likes a product? And then the very last topic that we want to consider it in this area. We've been primarily thinking about confidence intervals, which we use to describe, right, what a population parameter is. That's different from trying to make a prediction about what a population parameter will be, right? Fundamentally, a confidence interval is in a sense looking at this current time period. What's the interval estimate of our current population, whereas a prediction is trying to talk about that uncertainty of our population parameter and also making a projection about it, right? It's a prediction. And so there's a little bit extra uncertainty involved with doing prediction intervals. And you may have calculated these before. If not, it's not really that big of a difference. CI for confidence interval, PI is common for a prediction interval. We're just simply predicting values of new observations with a given sample, right? So we're going beyond our sample, not describing our sample, but trying to predict a value. We've still got X bar, assuming that we don't know our underlying population parameter value of standard deviation, which we often won't. We still got a T. We've still got our sample standard deviation, but now here's the difference, right? In the past, we had S over square root of n, which I could write as S times 1 over square root of n. And I want to do a little bit of algebra and say that, hey, I can, what am I doing here? Instead of having 1 over square root of n, I'm taking the square root of 1 plus 1 over n. And notice that I could, right, this is the way that we have been calculating it, I could rewrite that as well as s times the square root of 1 over n, right? With this prediction interval, we don't have s times square root of 1 over n. We've got s times 1 plus 1 over the square root of n. We've added a little bit more of a value to our margin of error to capture this additional uncertainty because we're making a prediction. Rather than just doing a confidence interval about what our sample is, we're making our prediction. So it has a little bit more uncertainty associated with it. Mathematically, all we're doing is just adding in a little bit of an extra value there, right? And again, this formula should be pretty straightforward. You should just be able to crank through and find those different pieces based on everything else that we've discussed so far. I've alluded to this a few times in the past in this topic, but now to be more formal about this, right? Everything on the right-hand side of the plus or minus, we refer to that as the margin of error. Not just this formula, but any of the formulas that we've looked at. Whatever is to the right of the plus or minus is what we refer to as the margin of error. Sometimes that margin of error, let's call it E, we might want to have a specific value of margin of error. When you're dealing with a client, they might request a certain amount of specificity with their confidence interval. What they're really describing is the size of their margin of error. And what we can do is we can find, if we want to achieve a certain level of margin of error, this is not something we can control. This is not something we can control, but this is something we can control, right? If you're carrying out a bunch of market research, if you're sending out a bunch of surveys, the number of observations that you have, you can control that by sending out more surveys, right? So that all costs money though, right? As we send out more surveys, as we increase the number of observations that we get in our sample, it's going to reduce the size of a margin of error, right? So there's this trade-off, right? Your boss or your client or you yourself, you may want a certain small margin of error, but the only way that you're going to be able to achieve a small margin of error is by incurring a cost for achieving more observations. So oftentimes you're trying to balance those two forces of reducing your margin of error against spending the money on getting more observations. What we can also do though is if we know specifically that we want a margin of error to be 0.05, we can use this other information and a little bit of algebra to find what the value of n would be that would achieve this margin of error.